In our previous classes, we discussed the basis of differential calculus. I give a table that's a table of functions and their derivatives that I personally think that the moment someone absorbs the table, he already knows the reasonable percentage of differential calculus, because you always have to make reference to those derivatives as it were. So, but today I just want to give some simple examples that we can solve in differential calculus, the likes of chain rule, product rule, quotient rule, function of functions, implicit function. Should in case I couldn't complete the whole of what I mentioned now, it may mean that I will split it over to the next class. But let's see how it goes. So I just want to make us get familiar with that table of function and how it works as it were. So if you remember, we said that given a function f of x, let's say is equals to y, when I differentiate this, I can write it as dy dx becoming f prime of x. So I can also write this as y prime equals f prime of x, as the case may be. These are just called the way we denote differentiation. That means derivative of x with respect to y or y with respect to x, as the case may be. You understand? So, but we are going to be taking some simple examples like the differential of a polynomial function, which I believe we are going to talk about polynomial in this too. So we have a polynomial function, what do I expect? But let me therefore reiterate this to you, that if I have something of the form y equals x raised to the power of n, do not forget that this will just become dy dx is equals to n comes to the back, and then have n raised to the power n minus 1. There is a method of proving this using the first principle and the binomial theorem principle is also brought into it, but not to talk for today. So let's take an example. Just put it to parts. When I'm taking, this is called first derivative actually, you understand? That's first derivative. If I want to take my second derivative, it means I'm dividing this one twice. It becomes d squared y over dx squared, and then it becomes n is here already before. This one will come to the back, and then become n minus 1. Now we have x raised to the power of n minus 2, because it will become minus 1 minus 1. If I'm going in third time as well, it's still the same process. It's going to become what? It's going to become, this one comes to the back again. These guys are constants. It becomes n minus 1, then n minus 2. Then I have x raised to the power n minus 2 minus 1. So it becomes n minus 3. And that is how it goes on and on and on, just for you to observe. So if you are now asked to, maybe for example, you are asked to differentiate the following, what I'm trying to mention now, number one, you have to differentiate the following. How am I going to get it done? Differentiate the following. Number one, I have say y equals, that means I have 3x squared. Number two, I have y equals minus 4x raised to the power minus 1. And number three, I have say y equals x raised to the power 3 minus 2x squared, say plus 5. Yes, let me add number 4 to hit. I have y equals, this is just derivative, a polynomial function, like, you understand? Though this one is not polynomial. They want to still give us questions that look in form of a polynomial, and they have the same method of solution. So look at that. Number one, okay, number 4, I have, I have 2x raised to the power of 5 minus, let me say sine x, and let me say plus e raised to the power x. So let me add 10 to it. What am I going to be having when I solve this kind of question? So do not forget, this question, any question in this similitude is applied in this form, and this method is what we are going to be solving them, depending on if I solve for the first derivative, the second, the third, or the nth derivative. But definitely for this class, we're only focusing on the first derivative we have to get ourselves used to that before we can go any further. So look at that. Look at the problem. Let's take a solution. Solution. Look at the problem. We have y equals 3x squared. Then it becomes dy dx equals 2 times 3. So it becomes 3 times 2, like I said. Then write the x, then that's 2 minus 1. Just the same arbitrary there. The 3 has already been a constant. So 3 times 2 is 6. And I have x raised to the power 1, which is the same as 6x. Because anything raised to the power of 1 is still that same thing. Now look at number 2. I have y equals minus 4x raised to the power minus 1. Just the same principle. Now of course a constant. So dy dx will just become minus 4 in the bracket. Then minus 1 will come to the back. Then I write my x saying minus 1 minus 1. Do you understand? Then this becomes minus 4 times minus 1. That is simply 4. Then I have x raised to the power minus 2 as my answer. So let's try number 3 as well. The same, there's nothing difficult, just follow the pattern and flow. Look at number the y part, I have x to the power of 3 minus 2x squared plus 5. Then when I want to differentiate, it becomes dy dx, and that's equals to 3 comes back, it becomes 3x, 3 minus 1. Then 2 comes to the back, but this time it's minus 2. Minus 2 times 2, then x, 2 minus 1. And when you multiply a constant, it gives you 0. If you check that table, you'll find that there. So I then have y prime. Don't forget that y prime is the same as y dx. So I have 3x all raised to the power what? 2. Then minus 2 times 2 minus 4x raised to the power 1. And that's my answer, eventually. So look at, let's just solve number 4 here. Look at number 4. Just, I don't want to write before, I want to see. Look at number 4. Well, let me just solve it straight. I want to solve dy dx of this number 4. What do I have? 5 times 2. So 2 times 5x, 5 minus 1. When you differentiate sin x, what does it give you? Reference to that table. It gives you minus cos x. I mean, it gives you cos x. When you differentiate sin x, it gives you cos x. It's minus x. Then plus, when you differentiate e raised by x, it gives you e raised by x. That's a smooth function. It gives you e raised by x. No matter how often you differentiate it. Then when you relate to cos plus 10, which is a constant, it gives you 0. So eventually, what will answer be? It becomes 10x all raised to the power of what? 4 minus cos x plus e raised to the power x. And that's how simple it can be. You understand the process. So you see why I made reference to the table. From that table, we discover what the value of sine will be when you differentiate it. What will be when it is e raised to the power x. So you can make reference to it once again for better clarity. You understand? So, but we're going to, this is as simple as it can be. Yes, I don't care how long it is, I don't care as long as it is in this form, having possibilities in the middle, that's how I'm going to get it without any stress. But the next one I'm going to take us through now is what we call the function of function. It's also simple. We only need to follow the normal process. So we'll be fine. So just stay with me. Okay, we're going to be looking at function of function now. And the concept of function is having a function that is a function of another function. And it has a way of differentiation. What I mean is this. Imagine you have the function y, you get that is the function of u, and this u is the function of x. You know what I'm saying? Something like this, something like saying y equals f of u of x. So you get, it's like saying that pot of pots, like you can see a big pot, inside that big pot there's another pot, inside this pot there's another pot. This is pot of pot because we keep stacking pot into pot. So, but because I've fixed a function into another function, we call it function of functions. So, and there's a way to get that done. Do you understand? So, if I have an equation, a function of this form, then my dy dx is simply going to be, please keep this to heart, is going to be dy du, that is, I am differentiating this my y with respect to u, then multiply by du dx, and differentiate my u with respect to x. If I slice it out here now, I will have the y dx back. So it's just a simple concept that one can easily absorb. So keep that part, that when you have a function of this form, this is how it's going to go. And even if it happens to be of this form, such that, let me have another thing to it, so that x is a function of w, so that if I have a function, say y equals a function of u, and x is a function of w, this time, like I've written here, like a function of function, then like dy, d what, dx, will simply become dy, d what, du, times du, dw, times dw, dx. This will have been my formula for solving, and that will have my dy, du, then du, dw, then dw, dx, and that will be how I'm going to solve it eventually when I have a function. So it doesn't matter how robust it looks like, there's a way to solve it. So I want to take an example of this one now and see how it goes. Okay, let's solve our 3 questions now. Question, I look at the 3. The third part of it, number 3. We have I have y equals to, it's very simple to solve now, x squared minus 1 all raised to power 4. Let what? Let u equals to x squared minus 1. Then what happened? Y equals u raised to power 4. Du dx is now what? Du dx is simply equals to 2x raised to power 1. Then is 0. Then dy du is what? Dy du is simply equals to 4u raised to power 4 minus 1. And that is 4u raised to power what? 3. You get the gist? Then what do you recall? You recall that dy dx is equals to what? Dy du times du dx. That means your dy dx is still y prime, same thing because of the notation. And your dy du is what? 4u raised to power 3 times du dx, that is 2x. So when I multiply these two guys together, it becomes 8x u raised to power 3. Then 8x, what is my u? My u is x squared minus 1, so I will say x squared minus 1 all raised to power 3. And that's my answer. What if I do not use this long method? The same thing. Remember we did this, or the redo. Write the 4 to the back, then differentiate what you have inside, 2x, write it back, x squared minus 1 minus 1, that is 3. So I have 8x, this back, then 3. So let's just split this back. So let's take the fourth one, look at the fourth one, the same way, and nothing is actually changing as it were. Just the same way. Look at number 4. I have y is equals to what? Sine 2x squared plus 1. So I will say what? Let u be equals to 2x squared plus 1. Then my y will be equals to what? Sine u. Then du dx is now equals to 4x. This becomes 0. Then dy du becomes cos u. From that table, that's the reference table now, when you just sine u, this is cos u. So I will then say that my dy dx is then equals to what? Dy du times du dx. Is it making sense? So that means y prime is equals to dy du equals to cos u times u dx is what? 4x. Multiply together, y prime equals 4x cos u. But what is u from concept? So my y prime equals to 4x cos u. Cos, what is my u? My u is in brackets 2x squared plus 1. And that will be my answer. What if I want to go for the short method? It will have been come here, differentiate what I have inside. That will be what? 4x. Then differentiate sine, this means cos, then write it back. This means 2x squared plus 1. Answer without stress. So it's just to understand the reading and flow that reading becomes easier as it were. So let's try this without solving the long method. I'll just give you the answer and I will see you try it and put your answer in the comment box. So I'm going to try the reading method to solve it. Look at y. Y equals e raised to power 5x squared plus minus ex. So what do? I come to the numerator, I turn it to u. So I play this guy, it becomes 10x minus e raised to power x. E raised to power, then I'll write I will write this back because when you integrate e, it still give you e raised to power, write it back. 5x squared minus ex. When you solve it, you should have this as your answer. Try trying it and try other questions as well extensively to discover that it is not difficult to know. So in our last class, probably I'm going to be looking at the function of the product rule and the quotient rule. Then I'll tell you what are the things you look out for to know that I'm going to be using this method or that method, just for us to understand the basis and from there we build on. Thank you for being a part of this class. Do well to press the notification bell and subscribe, and I'll see you in the next class. Thank you.